Okay, so one way or another, the bacteria gets in. That's not always the end of the story. It has to get in the proper way. In other words, if it's supposed to come in through the door, climbing through the window does not work. So usually a preferred port of entry, they enter the wrong way, no disease. My example here is salmonella. Now everybody knows salmonella causes food poisoning. But if you rub it on your skin, even if there's a cut there, if you rub it on your skin, you don't get food poisoning. It's got to go through your digestive tract. If it goes in some other way, nothing happens. So again, not just getting in, it's got to get in the right way. Number of cells. You know, we've all had the occasion that you're sitting next to somebody who's coughing and sneezing and you're kind of moving away because you know you're doomed. And then you actually don't get sick. And it might be that you weren't exposed very much, very small number of cells. And essentially, your immune system can fight it off. It happens. So the number of cells, the amount of exposure can be a factor. However, if you have a large exposure, you better go out and buy Kleenex because you're going to get sick. The point is, lots of different things influence. Are you going to get sick or not? Adherence. The bacteria needs to be able to stick to the cell before it invades. So bacteria often have adhesins or ligands that stick to the receptors on the cell. So these adhesins or ligands that will be doing the sticking, it should not surprise you to know that in all likelihood, these are glycoproteins. We run into those things all quarter. You know the story, information molecules or stickiness, in this case, stickiness. But again, they're called adhesins or ligands. These are on the bacteria. They will use them to stick to the cell, the host cell. Capsules. We're just doing factors here, influences. Many capsules enhance the virulence of the species. I don't think I've used that word before, but virulence can mean one of two things. Generally, it means how sick are you going to get. The more virulent something is, the more sick you're going to get. But it can occur from two different reasons. One is the virulence indicates when you're exposed, how often you get sick from that. So if you only get sick maybe 5% of the time when you've been exposed, then you would say it's not very virulent. If you get sick 80% of the time, that's pretty virulent. So virulence can indicate what percentage of the time you get sick when you've been exposed. A second possibility is when you get sick, how sick do you get? If you get really sick, again, that would be virulent. If you really don't get sick, you're sick, but you're kind of okay. That's not very virulent. So two possible definitions for virulence, both just simply indicating how sick are you getting. One is how often do you get sick when you're exposed, and second, how sick do you get once you've been exposed. Both of those would be virulence. The capsule, if you remember, we talked about pneumonia bacteria, and the capsule can resist macrophages, can resist being swallowed, because the capsule will be too sticky. I'm sorry, wrong. It will be too slippery. The capsule will be too slippery, the macrophage cannot grab it. We talked about that with pneumonia bacteria. essentially, if the macrophage can eat the bacteria cannot make you sick. To the capsule, the cell will escape the macrophages. They do not get eaten, and therefore they do make you sick. But, just because we get infected with an encapsulated bacteria, it does not mean we die. We do have antibodies, so we might get sick, but eventually we will get rid of the bacteria. Antibodies can be produced against the capsule. The antibodies stick to the capsule. The macrophage can then stick to the antibodies and the cell. Basically, there's always second and third lines of defense here. If one defense fails, the immune system brings in something else. Streptococcus pneumonia is the one we talked about a while ago. Needs a capsule. Without the capsule, the macrophages eat them. No pneumonia. With the capsule, they escape and they don't get eaten, so they cause pneumonia. There are other encapsulated bacteria. Anthrax, well, those aren't bacteria, but they cause diseases, anthrax, meningitis, bubonic plague. Those all require capsules, just like pneumonia does. But that's not always the case. There are some virulent or pathogenic bacteria that do not need a capsule. So they have other defenses. It's just not a capsule. Cell walls of some bacteria contain chemical substances to aid environments. Streptococcus pyogenes, these are the guys that eat red blood cells. They contain a heat-resistant, acid-resistant protein called M protein. So resist acid, resist heat. Also helps phagocytosis, and it helps in attachment. It's a pretty good protein.
So does that make it a thermocytophile?
I'm sorry?
Does that make it a thermocytophile?
No. It's showing the same symptoms, but it's not a thermocytophile, because that would be an archaebacteria, and that's not these. But, so that shows the same symptoms is coincidental. So just simply an example of another variation that capsules are not always needed to achieve the same purposes. Various enzymes can aid in virulence. Again, the virulence means how sick you get, how often you get sick. So various enzymes can help. Leukocyte, leuko means white blood cell. For example, you're all familiar with leukemia. Leukemia is a cancer of the white cells. Poseidon means to kill. Homicide, suicide, genocide, that means to kill. So leukocytins, the name itself is telling you, is killing white blood cells. Hemolysins, you can kind of guess this one. Hemoglobin, lysin is to rupture. So these guys, these enzymes, are going to rupture red blood cells. Coagulases. This is an odd one. This is an odd thing. They clot fibrinogen. Let me back you up just a little bit. Fibrinogen is one of the last molecules in the pathway for clotting the blood. Fibrinogen will actually be broken down a little bit to produce fibrin. Fibrin produces the clots. So basically, these coagulases are causing blood clots to form. The bacteria then hides inside the blood clot. So by hiding inside the blood clot, let me say here, the macrophages cannot get the bacteria. Again, unusual, it's weird. So again, the coagulases are enzymes. They cause blood clots to form, and the bacteria then hides inside the blood clot. The macrophage cannot get there. Once again, though, we always have counterattacks. Kinases. Now, normally, as you well know, kinases will transport phosphate groups, will transfer phosphate groups. In this case, they break down the fibrin. The fibrin, remember, is supposed to make the blood clot. So by breaking down fibrin, they're breaking down the blood clots. Therefore, the bacteria can no longer hide, and the macrophages come to guess them. So again, the coagulases form blood clots, the bacteria hide in the blood clots. The kinases, in this case, break down the blood clots, and then the macrophages can come get the bacteria. Damaging cell walls. Sometimes bacteria will directly penetrate the host cell wall if they're attacking bacteria. Or, of course, in our case, no cell wall, so they can directly penetrate our cell membranes. But either way, so direct damage to bacteria will directly penetrate the cell wall and or cell membrane and enter into the cell, and then can produce toxins. Toxins are poisons. Toxins are poisons. Toxins are why we get sick. Fever, diarrhea, and lots of other side effects. So think back now, what kind of toxins are produced by gram-negative cells? It's been a while. 50-50 chance.
Endotoxins.
Endotoxins. Because those stay in the cell. So endotoxins are made by the gram-negative, and therefore the exotoxins are made by gram-positives. Toxins in general can also inhibit protein synthesis. Now what that means is, in inhibiting proteins, can be inhibiting enzyme formation. And that means might be interfering with metabolism, because that can make you sick. Can destroy blood cells, that will make you get tired because not carrying enough oxygen. The exotoxins are coming from gram-positive, so they are being released from the cell. They will destroy parts of the host cell. Now specifically here, cytotoxins. Now these are all exotoxins. They're all coming from gram-positive. So the cytotoxins are going to destroy the cells themselves. Neurotoxins interfere with nerve cell transmission. See, that's what happens with Clostridium. I mentioned how Clostridium can cause tetanus. Tetanus is when you contract your muscles, you cannot release, you cannot let go. The neurotoxin from Clostridium blocks the nerve transmission saying, relax your muscle. Enterotoxins, so all of those various bacteria that live in the, well, I shouldn't say all of them, because some are gram-negative, so never mind. Some of the bacteria living in the digestive tract can form enterotoxins. So some are gram-positive, some are gram-negative. I misspoke. Again, all of these are coming from gram-positive. They're all exotoxins. And as is always the case, the body will produce antitoxins to fight the toxins. Just like we have antibodies to fight antigens. Either the immune system fights off the infection or we die. Those are the choices. And usually, of course, the immune system wins. Usually. The endotoxin, of course, are gram-negative. Specifically, I have it here, I do not. Do you remember what part of the cell wall is forming the endotoxin?
No,
You're going to look at your notes, I can see it.
no, I know.
Okay. Do you remember? Lipid A.
Yeah,
Lipid A. Yeah. So anyhow, that's the endotoxin, part of the cell wall in the outer membrane. So the outer membrane has those lipopolyproteins, the lipopolysaccharides. There we go, lipid A is forming the endotoxin. Do you remember what part of the cell wall in the gram-positive cell gives you the antigenic specificity? What part of the cell wall allows the immune system to identify what kind of bacteria you have for gram-positive? Teichoic acids. Teichoic acids. So what part of the cell wall in the gram-negative cell does the same thing? Those would be the O saccharides. The O saccharide, yeah, the lipopolysaccharides. So the O polysaccharides, I guess you should say. Okay, anyhow, so lipid A is your endotoxin. Exotoxins are proteins.
Why is that under?
I'm sorry,
I'm just wondering why is that under endotoxin?
I'm just comparing with the
Oh,
endotoxin.
okay.
I just comparison.
Okay.
There's no ulterior motive. All endotoxins do the same thing. Chills, fever, weakness, ache, shock. They all have the same symptoms. Okay, you've all heard the term shock. What exactly is shock? It's not something we've done. I'm just wondering if you know or not. Anybody know what shock is? It's a sudden drop of blood pressure. A sudden drop. So maybe bad news, you know, we've all heard those, seen those stories. Some heard bad news and fainted or whatever. Might be sunstroke or something. Basically, a sudden drop of blood pressure. The blood pressure is not strong enough to send blood back to the brain, so you faint. If somebody's ever in shock, then get his legs above his head so the blood goes back to the head. He'll probably be cold, even on a hot day, because of the lack of blood flow. So maybe put a blanket or a jacket on him or something, and keep him warm, and the legs above the head, get the blood back. Oh, done. I can tell you we're not too excited, because that is number 2 out of 5, so there's 3 more to go. So let's switch gears. Let's see, after I turn off the recording.